there's a mirror universe. Let me be precise about what that sentence means, because the specific theoretical proposal it is pointing at is a real, peer-reviewed, intellectually serious piece of theoretical physics published in one of the most prestigious journals in the field, and it deserves a specific, accurate account that is more interesting than the dramatic version and more honest than the sensationalized framing implies. The specific proposal is not that scientists have discovered a parallel universe existing alongside ours in some higher dimensional space, accessible through a specific portal or detectable by some specific instrument. It is not the many worlds branching of quantum mechanics, not the inflationary multiverse of bubble universes, not the string landscape of 10,500 vacuum states. It is something more specific, more mathematically precise, and more directly connected to the specific fundamental symmetries of physics, and those connections are what make it genuinely interesting. In 2018, Neil Turok and Latham Boyle at the Perimeter Institute for Theoretical Physics in Waterloo, Canada, published a specific paper in Physical Review Letters proposing that the universe we inhabit may be one half of a specific CPT symmetric pair. The specific acronym stands for charge, parity, and time, the three discrete symmetries of quantum field theory whose specific combined action is believed to be an exact symmetry of all fundamental physics. The specific CPT theorem, one of the most rigorous and most thoroughly tested results in quantum field theory, says that the laws of physics are invariant under the simultaneous reversal of charge, the reversal of spatial parity, and the reversal of the direction of time. Turok and Boyle's specific proposal is that the Big Bang itself is a CPT symmetric event, that the solution to the cosmological equations that describes our universe, our specific expanding universe filled with our specific matter, evolving in our specific temporal direction, has a specific CPT partner, a universe of antimatter, expanding in the opposite temporal direction, which is the specific mathematical image of our universe under the combined CPT transformation. Not a universe that exists somewhere else in space. A universe that is, in a specific mathematical sense, the other side of the Big Bang, extending backward in time from the moment of the Big Bang in the same way that our universe extends forward. The Big Bang is not a beginning at one end of a timeline. In this specific model, it is a specific symmetric point, a specific moment of time reversal symmetry from which two universes extend in opposite temporal directions. This is the specific mirror universe that the Turok-Boyle proposal describes. And understanding what it actually implies, what predictions it makes, what evidence would support or refute it, and how it connects to the specific deepest questions about CPT symmetry, dark matter, and the arrow of time is more interesting than any clickbait framing can convey. Let me start with the specific physics of CPT symmetry, because understanding this symmetry is the foundation for understanding why the Turok-Boyle proposal is taken seriously by physicists. CPT symmetry is the specific combined operation of three distinct, discrete transformations. Charge conjugation C replaces every particle with its specific antiparticle. Every electron becomes a positron. Every quark becomes its specific antiquark. Every positive charge becomes negative, and vice versa. Parity reversal P reflects all spatial coordinates through the origin, replacing every left-handed coordinate system with a right-handed one, effectively mirroring the universe. Time reversal T replaces T with minus T, running all physical processes backward. Individually, these three symmetries are each violated by specific aspects of the known physics. Parity violation in the weak nuclear force was famously discovered by Chien-Shiung Wu in 1957, the specific observation that radioactive cobalt, 6-0 decays, preferentially emit electrons in the direction opposite to the nuclear spin, which is a specific handedness-dependent effect that cannot occur if parity is conserved. Charge conjugation is similarly violated by the weak interaction. CP violation, the combined violation of charge conjugation and parity, was discovered in kaon decays in 1964 and in B meson decays more recently, and is directly connected to the specific matter-antimatter asymmetry of the observable universe. But CPT, all three together, is an exact symmetry of every specific quantum field theory consistent with Lorentz invariance. The CPT theorem, proved rigorously by Wolfgang Pauli, Gerhard Lüders, and others in the 1950s, establishes that any Lorentz invariant local quantum field theory must be CPT symmetric. Violations of CPT symmetry would require specific modifications to quantum field theory at a very fundamental level, and every specific experimental test of CPT symmetry conducted across every specific accessible energy scale has confirmed it with extraordinary precision. The specific Turok-Boyle proposal takes this exact symmetry seriously as a cosmological constraint. If CPT is an exact symmetry of the laws of physics, they argue, it should also be a specific symmetry of the specific solution to those laws that describes our universe. The universe as a whole, not just the local dynamics, not just the particle interactions, but the specific global structure of space-time and its specific matter content, should respect CPT symmetry. And when you impose this specific requirement on cosmological solutions to Einstein's equations in the presence of specific quantum fields, the specific result that emerges naturally is the paired universe structure. Our universe, paired with a specific CPT image that extends in the opposite temporal direction from the Big Bang. Let me now take you to the specific content of what the CPT partner universe would be like, because the specific properties are both remarkable and specific. The CPT operation applied to our entire universe reverses three things simultaneously. It reverses all charges, every specific proton in our universe, made of specific quarks with specific color charges and specific electric charges, becomes a specific antiproton made of specific antiquarks with specific opposite charges in the partner universe. Every specific electron becomes a specific positron. Every specific atom made of specific matter becomes a specific atom made of specific antimatter. It reverses parity. The specific spatial handedness of every specific physical configuration is flipped. Every specific left-handed neutrino in our universe becomes a specific right-handed antineutrino in the partner universe. And it reverses time. The specific direction of temporal evolution in the partner universe is opposite to ours. From the perspective of our universe's time coordinate, the partner universe extends in the direction we call the past from the Big Bang, while our universe extends in the direction we call the future. The specific result is a universe that is, from our perspective, an antimatter universe running backward in time. But, and this is the specific, crucial, and most interesting point from the perspective of observers within the partner universe, everything is perfectly normal. Their specific laws of physics are identical to ours, because CPT transformation maps our laws to theirs identically. Their specific matter is made of specific antiparticles relative to ours, but their specific antiparticles are their specific matter. There is no asymmetry from within. And their specific time runs forward from their perspective, even though from our perspective it runs backward. This specific self-consistency, the specific fact that the CPT partner universe is a specific, perfectly valid, physically consistent universe with specific observers who experience normal physics, is what distinguishes the Turok-Boyle proposal from a mere mathematical curiosity. It is not a universe that violates the laws of physics. It is a universe that respects precisely the same laws of physics as ours, related to ours by the specific, most fundamental, discrete symmetry of quantum field theory. Let me now take you to the specific, most important, and most testable prediction of the Turok-Boyle model, the specific connection to dark matter and neutrinos that made the proposal immediately scientifically interesting when it was published. Our universe has a specific matter-antimatter asymmetry. There is approximately one extra baryon, one extra proton or neutron for every specific billion photons in our universe. The specific remaining baryons annihilated with specific equal numbers of antibaryons in the early universe, leaving the specific residual 1 in a billion excess of matter that constitutes all the specific galaxies, stars, planets, and living organisms we observe. The specific origin of this asymmetry, why there was one extra baryon for every billion baryon-antibaryon pairs in the early universe, is the specific baryogenesis problem, one of the specific central unsolved problems in cosmology and particle physics. In the Turok-Boyle framework, the baryogenesis problem has a specific natural interpretation. The specific apparent matter-antimatter asymmetry in our universe is not a specific asymmetry of the universe as a whole. It is a specific consequence of CPT symmetry. Our universe has specific matter. The CPT partner universe has specific antimatter. The combined system is CPT symmetric. The specific total charge of both universes together is 0. From the perspective of the complete CPT symmetric solution, there is no asymmetry. Each universe is the specific mirror of the other. But the specific, most immediately testable prediction involves neutrinos and dark matter. In the standard model, neutrinos are specific left-handed massless particles, but the specific observed neutrino oscillations, the specific phenomenon in which neutrinos of one flavor transform into neutrinos of a different flavor as they propagate, require neutrinos to have specific non-zero masses. This specific requirement extends the standard model. It requires specific additional neutrino states not present in the minimal standard model. Turok and Boyle's specific model predicts that the specific additional neutrino states required to give neutrinos mass are specific right-handed neutrinos. The specific particles that are the CPT partners of the specific left-handed neutrinos in our universe, these specific right-handed neutrinos, often called sterile neutrinos because they don't participate in the specific weak interaction, are the specific bridge between our universe and its CPT partner. And here is the specific, most remarkable prediction. In the Turok-Boyle model, these specific right-handed sterile neutrinos produced at the Big Bang through the specific CPT symmetric dynamics of the cosmological evolution are the specific dark matter. The specific invisible mass that makes up approximately 27% of the universe's total energy density, that shapes the specific cosmic web, that enables the specific formation of galaxies in the Turok-Boyle model, it is specific sterile neutrinos produced at the Big Bang through the specific dynamics of CPT symmetry. This is a specific, concrete, testable prediction, not a vague gesture toward naturalness or aesthetic beauty. A specific particle species, sterile neutrinos, with specific mass range constraints, approximately 10 to 1,000 mega-electron volts, that can be searched for with specific experimental techniques. Let me now take you to the specific experimental and observational constraints on the Turok-Boyle model, because this is the specific, most important question for evaluating any theoretical proposal. The specific, most direct test involves the specific mass and mixing properties of the sterile neutrinos predicted to be the dark matter. In the Turok-Boyle model, the specific sterile neutrino mass is constrained by the specific requirement that its specific relic density, the specific number of sterile neutrinos produced at the Big Bang through the specific CPT mechanism, matches the observed dark matter density. This specific constraint gives a specific preferred mass range of approximately 10 mega-electron volts to several hundred mega-electron volts, depending on the specific details of the model. Sterile neutrinos in this specific mass range would decay through specific processes, most importantly, through the specific decay into an active neutrino and a specific X-ray photon. The specific X-ray photon would have a specific energy equal to half the sterile neutrino mass for a specific 100 mega-electron volt sterile neutrino. The specific X-ray would have specific energy of 50 mega-electron volts in the specific high-energy X-ray range. If the dark matter in galaxy halos and galaxy clusters is specific sterile neutrinos decaying into specific X-rays, the specific X-ray observatories, the specific Chandra X-ray observatory, the specific XMM Newton satellite, the specific planned Athena mission from ESA should detect a specific monochromatic X-ray line from specific directions with specific high dark matter density. The specific 3.5 keV line, a specific anomalous X-ray emission feature detected at specific 3.5 kilo electron volts in specific multiple X-ray observations of galaxy clusters and the Milky Way center by specific multiple independent research groups, was briefly interpreted as a specific possible sterile neutrino decay signal when first reported in 2014. Subsequent analysis has been specific and contested. Some specific observations confirm the specific line, others do not, and the specific systematic uncertainties in X-ray spectroscopy make the interpretation genuinely ambiguous. The Turok-Boyle sterile neutrino dark matter predicts specific X-ray signals in the specific multi-mega electron volt energy range higher than the specific 3.5 keV anomaly, that specific future. X-ray observatories with specific improved sensitivity could detect. The specific cosmological constraints are also relevant. The specific warm dark matter models in which dark matter has a specific non-zero thermal velocity that suppresses small-scale structure formation apply to the specific sterile neutrino masses predicted by the Turok-Boyle model. The specific Lyman alpha forest observations, which constrain the specific power spectrum of matter fluctuations on specific small scales, place specific lower limits on the dark matter particle mass in specific warm dark matter scenarios. The specific sterile neutrino mass range preferred by the Turok-Boyle model is in specific tension with some of the specific Lyman alpha constraints, though the specific tension depends on the specific details of the specific production mechanism. Let me now take you to the specific, most important recent theoretical development that has extended and clarified the Turok-Boyle proposal, the specific 2022 and 2023 papers by Boyle, Turok, and collaborators that have refined the specific predictions and addressed specific criticisms. The specific original 2018 proposal was developed in the specific context of a specific radiation-dominated early universe, with the specific CPT partner universe being a specific, relatively simple mirror of ours. The specific subsequent theoretical development has extended the analysis to include specific inflationary dynamics, asking whether the CPT symmetric cosmology can accommodate the specific inflationary epoch that is required to explain the specific flatness, isotropy, and specific structure of the observable universe. The specific result published in Physical Review D in 2022 is specific and interesting. The CPT symmetric cosmology can accommodate a specific inflationary epoch but the specific inflationary dynamics in the CPT symmetric framework have specific different properties from the specific standard inflationary models we discussed in the JWST and cosmic web conversations. The specific primordial power spectrum produced by the CPT symmetric inflation is specific. It makes specific predictions for the specific spectral tilt, the specific amplitude, and the specific non-Gaussianity parameters that are in specific tension with some aspects of the current CMB data and in specific agreement with others. This specific theoretical refinement is important because it moves the Turok-Boyle proposal from a specific qualitative scenario, two universes, one of matter, one of antimatter, to a specific quantitative framework with specific predictions for the specific, most precisely measured cosmological observables. The specific comparison with the specific Planck CMB data and the specific DESI large-scale structure data is the specific test that will most directly constrain or refute the specific framework. Let me now be specific about this specific important distinction between the Turok-Boyle proposal and the various other mirror universe or parallel universe scenarios that populate popular science coverage, because the specific distinction matters for understanding what is and isn't being claimed. The Turok-Boyle CPT symmetric universe is not a parallel universe in the specific multiverse sense. It does not exist at some specific spatial location beyond the specific horizon of our observable universe. It is not a specific bubble universe in an eternal inflationary landscape. It shares the same Big Bang as our universe. It is, in a specific mathematical sense, the specific other side of the same specific cosmological solution. The specific relationship between our universe and its CPT partner is more like the specific relationship between the specific two halves of a specific symmetric mathematical function than like the specific relationship between the specific two separate rooms of a specific house. The specific partner universe is not accessible. There is no specific portal, no specific wormhole, no specific causal connection. The specific Big Bang in this framework is a specific boundary of time, the specific point from which both universes evolve outward in their specific respective temporal directions without any specific causal contact. This specific inaccessibility is important for evaluating the proposal. We cannot observe the CPT partner universe directly, not because of any specific technological limitation, but because the specific causal structure of the model prevents it. The specific evidence for the model must come from within our own universe, from the specific properties of dark matter, from the specific properties of neutrinos, from the specific CMB power spectrum, and from the specific large-scale structure of the cosmos. This is a specific strength of the proposal compared to many other multiverse scenarios. It makes specific predictions that are testable within our own universe using specific instruments and specific observations that the current and next generations of experiments can perform. Let me close this first part with something that honestly frames the significance of the Turok-Boyle proposal, what it has achieved, what it has not, and why it deserves the specific scientific attention it has received. The specific proposal has achieved something genuinely important. It has identified a specific, physically motivated, mathematically precise scenario in which the Big Bang has a specific symmetric partner, not as an ad hoc addition to the cosmological model, but as a specific consequence of one of the most fundamental and most thoroughly tested symmetries of quantum field theory. It has derived specific predictions, sterile neutrino dark matter with specific mass ranges, specific X-ray decay signatures, specific cosmological structure formation signatures that are testable with specific current and planned experiments. And it has addressed the specific matter-antimatter asymmetry problem in a specific novel way, not through specific baryogenesis, but through specific CPT symmetry of the total universe. What it has not achieved is specific observational confirmation. The specific sterile neutrino dark matter prediction is not confirmed. The specific CPT symmetric inflations, specific CMB predictions are not definitively confirmed. They are in specific partial agreement and specific partial tension with the specific current data. And the specific theoretical framework has specific aspects, particularly the specific behavior near the Big Bang singularity that require specific further development. There's a mirror universe in the specific, technically precise sense of a specific CPT symmetric partner to our observable universe, extending in the opposite temporal direction from the Big Bang, composed of antimatter relative to our matter, making specific testable predictions about the specific nature of dark matter and the specific properties of neutrinos. Not in the sense of a specific accessible parallel reality, not in the sense of an alien civilization that is the specific mirror image of ours, not in the sense of anything that the specific dramatic framing implies, but in a specific sense that is more interesting, more physically grounded, and more testable than any dramatic version. The specific sense that the specific, most fundamental discrete symmetry of quantum field theory applied to the specific cosmological equations that govern the universe naturally generates a paired structure that looks from the inside of either universe like a single normal universe, but is, from the perspective of the complete CPT symmetric solution, always two. In part 2, I want to go deeper into what the specific CPT symmetric framework implies for the arrow of time and the connection to our earlier conversations about time's direction, into the specific neutrino mass predictions and how they compare to current neutrino oscillation data, and into something I find genuinely important, the specific way that the Turok-Boyle proposal connects to the specific deepest questions about why the universe has the specific properties it does. There's a mirror universe, specific, mathematical, testable, and the specific tests are underway. So we'd arrived at this place where the Turok-Boyle CPT symmetric universe proposal, published in Physical Review Letters in 2018 and extended in subsequent papers, is a specific, technically serious theoretical framework deriving a paired universe structure from the specific, most fundamental discrete symmetry of quantum field theory, where the specific CPT partner universe extends in the opposite temporal direction from the Big Bang, is composed of antimatter relative to our matter and is not accessible through any causal mechanism. Where the specific, most important testable prediction is that sterile neutrinos produced at the Big Bang through the CPT symmetric dynamics are the dark matter. And where the specific observational tests, X-ray decay signatures, neutrino mass constraints, CMB power spectrum predictions are ongoing. Now I want to go deeper into what the CPT symmetric framework implies for the arrow of time, into the specific neutrino mass predictions and how they compare to current experimental data, and into the specific connection between the Turok-Boyle proposal and several of the deepest questions this series has been addressing. Let me start with time, because the connection between CPT symmetry and the arrow of time is the most philosophically significant aspect of the proposal. we established in the arrow of time conversation that the direction of time's arrow is not written into the fundamental laws of physics. The laws are time symmetric, the Schrödinger equation, Maxwell's equations, Einstein's field equations all work equally well, run forward or backward. The arrow of time is a consequence of the specific initial condition of the universe, the specific low entropy Big Bang, not of any asymmetry in the laws themselves. The Turok-Boyle proposal adds a specific and important additional perspective on this question. If the universe has a CPT partner extending in the opposite temporal direction, then the arrow of time in our universe is specifically the CPT image of the arrow of time in the partner universe. From the perspective of the complete CPT symmetric solution, there is no preferred temporal direction. Both universes are equally valid, each running forward from the Big Bang in their respective temporal directions. This is a specific and elegant reframing of the arrow of time problem, not an explanation of why our universe has a low entropy initial condition. The CPT framework doesn't directly address that, but a specific demonstration that the apparent temporal asymmetry of our universe, the specific fact that time runs forward rather than backward, is a consequence of which side of the CPT symmetric solution we inhabit, not of any fundamental asymmetry in the laws. The specific connection to the quantum mechanical arrow of time we discussed is also direct. The specific quantum entanglement mechanism that produces the arrow of time, the specific flow of quantum information from local systems into their environments in the direction from the Big Bang forward, is the specific CPT image of the corresponding process in the partner universe. In the partner universe, quantum information flows in what we would call the backward direction, but from within the partner universe, this is simply forward in time. The CPT partner universe, therefore, has its own arrow of time, pointing in its own temporal direction, produced by the same quantum mechanical mechanism, but the two arrows point in opposite directions from the common Big Bang. The complete CPT symmetric solution has a specific temporal structure. Two arrows of time, each pointing away from the Big Bang in opposite directions, related by the specific CPT transformation that maps each universe to the other. This specific picture, two arrows of time pointing away from a common symmetric point, is philosophically striking. It suggests that the Big Bang is not a temporal beginning in any absolute sense. It is a specific CPT symmetric boundary, a specific moment of maximum symmetry from which the specific temporal asymmetry of each universe develops in its specific respective direction. The arrow of time problem in this framework becomes the question of why the CPT symmetric boundary has the specific properties it has, why the universe begins with low entropy on both sides of the Big Bang. This question is not resolved by the CPT framework alone. It remains connected to the specific quantum gravitational description of the Big Bang singularity that we discussed in the cosmological constant and quantum time reversal conversations. Let me now take you to the specific neutrino mass predictions, because this is where the Turok-Boyle model makes its most directly testable contact with current experimental data. The specific standard model of particle physics contains three species of active neutrinos: the specific electron neutrino, the specific muon neutrino, and the specific tau neutrino. All three are specific left-handed. In the minimal standard model, they are massless. But neutrino oscillations, the specific phenomenon in which a neutrino produced as one specific flavor transforms into another specific flavor as it propagates, require that the specific three active neutrino flavors have specific non-zero masses and specific non-zero mixing angles between the specific mass eigenstates and the specific flavor eigenstates. The specific experimental evidence for neutrino oscillations is overwhelming from the specific solar neutrino problem, the specific atmospheric neutrino anomaly, and specific dedicated oscillation experiments like T2K, NOVA, and the Diabet reactor experiment. The specific masses of the three active neutrinos are constrained by oscillation experiments to be non-zero but small. The specific mass squared differences are measured, giving specific lower bounds on the specific individual masses. The specific lightest neutrino mass could be essentially zero. The specific heaviest is constrained to be at most approximately 0.05 to 0.1 electron volts from oscillation data, and at most approximately 0.12 electron volts from the specific CMB cosmological constraints. The specific mechanism that gives neutrinos their mass requires extending the standard model. The specific most popular extension, the seesaw mechanism, introduces specific heavy right-handed neutrinos whose specific large Majorana masses produce, through the specific seesaw relationship, the specific small left-handed neutrino masses observed. The specific right-handed neutrino masses in the standard seesaw are typically extremely heavy, of order 10, 9 to 10, 15 GeV, far beyond any accessible experimental energy. The Turok-Boyle model predicts something specific and different. The specific right-handed neutrinos in their framework are the specific CPT partners of the left-handed neutrinos. They are produced at the Big Bang through the specific CPT symmetric dynamics rather than through the specific conventional thermal production. Their specific mass is constrained by the specific requirement that their specific relic density matches the observed dark matter density. The specific calculation gives a preferred mass range of approximately 10 mega-electron volts to several hundred mega-electron volts, enormously lighter than the specific traditional seesaw right-handed neutrinos, but much heavier than the specific active neutrinos. This specific mass range is the specific intermediate mass sterile neutrino regime. The specific compatibility with current neutrino oscillation data requires that the specific active neutrino masses, the specific masses of the left-handed neutrinos, be consistent with the specific oscillation measurements. In the Turok-Boyle framework, the specific active neutrino masses arise through a specific modified seesaw relationship involving the specific intermediate mass right-handed neutrinos. The specific calculation of the specific active neutrino masses from this mechanism gives specific predictions that are consistent with the specific current oscillation data for specific parameter choices, but the specific parameter space is constrained. The specific most important constraint comes from the specific normal versus inverted hierarchy of neutrino masses. Current oscillation experiments prefer the specific normal hierarchy. The specific lightest neutrino mass eigenstate has the smallest admixture of the specific electron neutrino flavor at a specific statistical significance of approximately 2 to 3 sigma. The specific Turok-Boyle model makes specific predictions about which specific hierarchy is preferred that can be tested as the specific oscillation experiment data improves. Let me now tell you about the specific experimental program most directly probing the sterile neutrino dark matter prediction of the Turok-Boyle model. The specific most sensitive current searches for sterile neutrino dark matter in the specific mass range predicted by the model use two specific approaches. The first is X-ray spectroscopy, searching for the specific X-ray photon produced when a sterile neutrino decays into an active neutrino. The second is specific structure formation constraints, comparing the specific observed abundance of small galaxies and the specific internal density profiles of dwarf galaxies with the specific predictions of warm dark matter models in the relevant mass range. The specific X-ray search is most directly relevant. A specific sterile neutrino of mass m S decays with a specific rate into a specific active neutrino and a specific X-ray photon of energy ms2. The specific decay rate depends on both the specific sterile neutrino mass and the specific mixing angle with the specific active neutrino sector, the specific parameter that determines how strongly the sterile neutrino couples to the standard model particles. For specific sterile neutrino masses in the specific 10 to several hundred megaelectron volt range, the specific X-ray photons would have specific energies in the specific tens to hundreds of megaelectron volt range, the specific high energy X-ray regime. Current X-ray satellites, Chandra, XMM, Newton, are optimized for specific energies of 0.1 to 10 kilo electron volts, significantly below this range. The specific planned Omega-X mission and the specific proposed COSI satellite are designed for specific higher energy gamma ray observations that would be sensitive to specific decay signals in this range. The specific most powerful constraint from current observations comes from the specific diffuse gamma ray background measured by the specific Fermi Gamma Ray Space Telescope. The specific non-detection of specific spectral features in the specific Fermi diffuse background limits the specific decay rate and therefore the specific mixing angle for sterile neutrinos in the specific mass range. The specific Turok-Boyle model must produce specific mixing angles consistent with the specific Fermi constraints, which requires specific parameter tuning that is not automatic but is not excluded. The specific structure formation constraints from the specific Lyman alpha forest are more challenging. The specific warm dark matter free streaming scale, the specific scale below which structure formation is suppressed by the specific thermal velocities of dark matter particle scales inversely with the specific dark matter mass. For specific sterile neutrinos in the specific 10 to 100 megaelectron volt range, the specific free streaming scale is smaller than the specific scales currently probed by the specific Lyman alpha forest observations. The specific structure formation constraints from the Lyman alpha forest, which require specific dark matter masses above approximately 5 kilo electron volts for specific thermal production mechanisms, may not directly apply to the specific non-thermal production mechanism of the Turok-Boyle model. The specific distinction between specific thermal and specific non-thermal production is important. In specific standard warm dark matter models, the specific dark matter particles are produced in specific thermal equilibrium in the early universe and have specific thermal velocity distributions that directly determine the specific free streaming scale. In the Turok-Boyle model, the specific sterile neutrinos are produced through the specific CPT symmetric dynamics at the Big Bang, a specific non-thermal production mechanism whose specific momentum distribution may be different from the specific thermal case, potentially evading the specific Lyman alpha constraints. Let me now take you to something that connects the Turok-Boyle proposal to several of the specific other anomalies and theoretical developments discussed throughout this series, because these connections suggest that the proposal is not an isolated theoretical curiosity, but is engaging with specific problems that multiple approaches are converging on. The specific connection to the dark matter problem is direct. We discussed the dark matter problem extensively, the specific elimination of WIMP candidates by direct detection experiments, the specific exclusion of fuzzy dark matter by the Subaru hypersuprime CAM results, the specific successes of MOND at galactic scales. The Turok-Boyle model predicts a specific dark matter candidate, intermediate mass sterile neutrinos, in a specific mass range that is not directly excluded by any of the current constraints and that has specific testable predictions in the specific X-ray and gamma ray bands. The specific connection to the matter-antimatter asymmetry problem is also direct. We've noted throughout this series that the specific observed matter-antimatter asymmetry, 1 baryon per billion photons, requires a specific explanation beyond the standard model. The Turok-Boyle model provides a specific alternative perspective. The asymmetry in our universe is the specific CPT image of the antimatter excess in the partner universe. The combined system is CPT symmetric. Within each universe, the apparent asymmetry is real. Our universe really does contain more matter than antimatter, but it is a consequence of CPT symmetry rather than of any specific baryogenesis mechanism. The specific connection to the cosmological constant problem is more subtle but real. The specific CPT symmetric cosmology has specific implications for the specific vacuum energy, the specific cosmological constant. In a specific CPT symmetric universe, the specific vacuum energy must satisfy specific symmetry constraints that limit the possible values. The specific, most natural CPT symmetric vacuum energy is 0, a specific result of the specific symmetric pairing of the specific positive and negative vacuum energy contributions from the specific two universes. But generating a specific small non-zero cosmological constant from this specific 0 natural value requires a specific mechanism that the Turok-Boyle framework has not fully specified. This specific connection between the specific CPT symmetry of the cosmological solution and the specific cosmological constant is one of the specific most interesting theoretical directions for extending the Turok-Boyle model. Let me now address a specific important objection to the Turok-Boyle proposal, one that is raised by physicists who take the specific mathematics seriously but question the specific physical interpretation. The specific objection involves the specific nature of the Big Bang singularity. In classical general relativity, the Big Bang is a specific singular point, a specific boundary of space-time where the specific classical equations break down and quantum gravity is required. The specific Turok-Boyle proposal treats the Big Bang as a specific smooth symmetric boundary, a specific moment from which two universes extend in opposite temporal directions without any specific singularity. But the specific classical Big Bang is not smooth. It is a specific singular boundary where the specific curvature diverges and the specific classical description fails. For the specific CPT symmetric pairing to work in the specific clean way the model requires, the specific quantum gravity description of the Big Bang must be specific smooth. The specific singularity must be resolved by the specific quantum gravitational dynamics in a way that allows the specific CPT symmetric extension across the boundary. This specific requirement that the specific Big Bang singularity be resolved by specific quantum gravity in a specific way compatible with the specific CPT pairing is not established. The specific quantum gravity description of the Big Bang is precisely what we discussed in the cosmological constant and quantum time reversal conversations as a specific central unsolved problem. The specific Hartle-Hawking no boundary proposal is one specific attempt, and Turok and collaborators have discussed the specific relationship between the CPT symmetric cosmology and the specific no boundary proposal. The specific resolution of the Big Bang singularity and the specific demonstration that the CPT symmetric pairing is compatible with the specific correct quantum gravitational description is the specific most important theoretical development needed to establish the Turok-Boyle proposal on a specific firmer footing. Let me now tell you about the specific observational programs that will most directly test the specific CPT symmetric cosmology prediction. Not just the specific dark matter prediction, but the specific imprint of the CPT framework on the specific cosmological observables. The specific most directly testable cosmological prediction involves the specific primordial gravitational wave background. In standard inflationary models, the specific inflationary epoch produces a specific background of gravitational waves, the specific tensor modes that imprint a specific B-mode polarization pattern on the CMB. The specific amplitude of this signal, characterized by the specific tensor to scalar ratio R, depends on the specific energy scale of inflation. In the Turok-Boyle CPT symmetric cosmology, the specific inflation must be consistent with the specific CPT pairing. The specific inflationary dynamics in this framework have specific different properties than the specific standard inflationary models in particular. The specific tensor to scalar ratio may be different. Some specific parameter choices in the CPT symmetric inflation give specific R values that are within the reach of the specific Lightbird satellite and the specific CMB S4 experiment. The specific next generation CMB polarization experiments designed precisely to detect or constrain the primordial gravitational wave background. If the specific Lightbird and CMB S4 detect a specific B-mode polarization signal with a specific R value consistent with the specific CPT symmetric inflation prediction, that would be a specific important confirmation of the framework. If they constrain R below the specific predicted range, the specific CPT symmetric inflation model would need specific revision or modification. The specific neutrino mass hierarchy determination is the specific other observational test most directly relevant to the model. The specific Dune experiment at Fermilab, the specific deep underground neutrino experiment, currently under construction, will determine the specific neutrino mass ordering with sufficient statistical power to distinguish normal from inverted hierarchy at specific high significance within the first few years of operation. The specific prediction of the Turok-Boyle model for the specific hierarchy can then be directly tested. Let me close this second part with something that situates the Turok-Boyle proposal in the specific, broader landscape of theoretical attempts to understand the deepest structure of the universe. Throughout this series, we've been encountering a specific pattern. The specific, most successful approaches to the specific, deepest problems, the specific black hole information paradox, the specific arrow of time, the specific cosmological constant, have involved taking the specific, most fundamental symmetries and principles of physics with specific, complete seriousness and following their specific implications wherever they lead. The island formula took the specific principle of unitarity with specific, complete seriousness and derived the specific mechanism of information preservation. The specific quantum mechanical derivation of the arrow of time took the specific unitarity of quantum mechanics with specific complete seriousness and derived the specific emergence of temporal asymmetry from quantum entanglement. The specific holographic principle took the specific connection between entropy and area with specific complete seriousness and derived the specific resolution of the information paradox. The Turok-Boyle proposal takes the specific CPT theorem, the specific most fundamental discrete symmetry of quantum field theory with specific complete seriousness, and applies it to the specific cosmological solution, deriving the specific paired universe structure. This specific approach is in the specific same spirit as the specific most successful theoretical developments in modern physics. It may be right. It may require specific modifications. It may be superseded by a specific more complete theory. But the specific approach, taking a specific fundamental principle seriously and following its implications, is the specific correct methodology for theoretical physics at the frontier. There's a mirror universe in the specific technically precise sense that the specific most fundamental discrete symmetry of quantum field theory applied to the specific cosmological solution naturally generates a specific CPT symmetric partner extending in the opposite temporal direction from the Big Bang. Not accessible, not observable directly, but making specific testable predictions about dark matter, about neutrino masses, about the primordial gravitational wave background, that specific ongoing and planned experiments will either confirm or refute. In part 3, I want to bring everything together into what the CPT symmetric universe means for our understanding of matter, antimatter, and time's arrow, and into what I think is the most profound implication of the entire story. There's a mirror universe. The specific evidence is theoretical. The specific tests are coming. So we'd arrived at this place where the Turok-Boyle CPT symmetric universe proposal, taking the specific, most fundamental discrete symmetry of quantum field theory with complete seriousness and applying it to the cosmological solution, generates a specific paired universe structure that is not a parallel dimension or an accessible alternate reality, but a specific mathematical partner extending in the opposite temporal direction from the Big Bang, where the specific, most testable prediction is intermediate mass sterile neutrino dark matter with specific decay signatures in the high energy X-ray and gamma ray bands. Where the specific neutrino mass hierarchy prediction is testable by the Dune experiment, and where the specific primordial gravitational wave prediction is within reach of LightBird and CMBS4. Now I want to bring it all the way home into what the CPT symmetric framework means for our understanding of why the universe has matter rather than antimatter, into the specific connection between this proposal and the deepest questions about time, symmetry, and the structure of physical law, and into what I think is the most important implication of the entire story. Let me start with matter and antimatter. The matter-antimatter asymmetry of the observable universe is one of the most precisely measured and least understood facts in cosmology. We know the asymmetry exists. Approximately 1 extra baryon per billion baryon-antibaryon pairs survived the specific annihilation epoch of the early universe. We know this specific asymmetry is real. Without it, the universe would contain only photons and no atoms, no stars, no planets, no observers. We do not know why it exists. The specific standard baryogenesis scenarios, electroweak baryogenesis, leptogenesis, Affleck-Dime baryogenesis, each invoke specific processes beyond the standard model that generate the specific asymmetry dynamically during the early universe's evolution. Each requires specific new particles or specific new interactions. None is established by direct experimental evidence. The specific LHC searches have not found the specific particles most natural baryogenesis scenarios predict. The Turok-Boyle framework offers a specific different perspective that deserves careful examination. In this framework, the baryogenesis problem is not solved, it is dissolved. The apparent asymmetry in our universe is not an asymmetry of the universe as a whole. The complete CPT symmetric solution contains both our matter universe and the antimatter partner universe. The combined baryon number is 0. CPT symmetry is preserved globally. This is a specific and important conceptual reframing, but it raises a specific immediate question that deserves honest treatment. From within our universe, the asymmetry is real. We observe only matter, no primordial antimatter. The CPT partner universe's antimatter doesn't cancel our matter from our perspective. The specific physical question, why does our universe appear to contain matter without antimatter, is not dissolved by pointing to the partner universe's antimatter. It is reframed as the question of why we find ourselves in the matter half of the CPT pair rather than the antimatter half. The specific answer available within the framework is straightforward. Both halves are equally valid, equally inhabited by observers, equally consistent with the specific laws of physics. Observers in our specific half observe matter. Observers in the partner half observe antimatter. Neither is privileged. The specific apparent asymmetry is a selection effect. We observe the matter half because we are in the matter half, not because the antimatter half doesn't exist. This specific anthropic element we observe matter because we're in the matter half is logically valid, but it doesn't eliminate the physical question of how the specific initial conditions at the Big Bang produce two specific separate halves, each with a specific definite matter or antimatter character from a specific CPT symmetric starting point. This specific question connects directly to the specific quantum gravitational description of the Big Bang singularity, the specific most important theoretical development needed. Let me now address the specific question of what it means for physical law that the universe might have a CPT partner, because this is where the philosophical significance of the proposal is deepest. CPT symmetry is not an accidental feature of the specific models we happen to have built. It is a specific mathematical consequence of two of the most fundamental principles in physics, Lorentz invariance and the locality of quantum field theory. The CPT theorem, proved rigorously within quantum field theory, says that any theory satisfying these principles must be CPT symmetric. You cannot violate CPT without abandoning either Lorentz invariance or locality, both of which are supported by overwhelming experimental evidence. When Turok and Boyle apply CPT symmetry to the cosmological solution rather than just to the local dynamics of particles and fields, they are extending this fundamental principle to its most natural domain, the universe as a whole. If the laws of physics respect CPT symmetry, and if the universe is a solution to those laws, the universe should respect CPT symmetry too. This is not a radical leap. It is the specific, most conservative extension of a well-established principle to the specific, broadest possible application. The specific radical move would be to say that CPT symmetry applies to all local processes, but somehow does not apply to the specific global cosmological solution, that there is a specific exception for the universe as a whole that doesn't apply to anything within it. The Turok-Boyle proposal is, in this specific sense, the specific, most conservative possible cosmology consistent with CPT symmetry. Not adding new fields, not introducing new mechanisms, not invoking new forces, just taking the existing symmetry completely seriously. Whether the universe actually respects this specific global CPT symmetry is an empirical question. The specific prediction, sterile neutrino dark matter, specific neutrino mass patterns, specific gravitational wave signatures are the specific tools with which the empirical question can be addressed. Let me now tell you about the specific broader context in which the Turok-Boyle proposal is most productively understood, its relationship to the specific research program of understanding the universe's initial conditions from first principles. Throughout the series, we've returned repeatedly to the specific question of why the universe began in a low-entropy, highly ordered state. The standard Big Bang model takes this as an initial condition, unexplained, simply assumed. The inflationary model addresses some aspects of it, explaining why the universe is so flat and smooth but not others, and potentially at the cost of introducing its own fine-tuning problems. The Turok-Boyle CPT symmetric cosmology is an attempt to derive specific properties of the Big Bang from specific symmetry principles rather than assuming them. If the Big Bang is a CPT symmetric point, a specific moment of maximum symmetry, then specific properties of the initial conditions are determined by the specific symmetry requirements rather than by arbitrary initial data. The specific, smooth, symmetric character of the Big Bang singularity in this framework is not an accident or a fine-tuning. It is a specific requirement of the specific CPT symmetry. This specific approach, deriving initial conditions from symmetry principles rather than postulating them, is exactly the approach that has been most successful in theoretical physics. The specific success of the CPT theorem itself in constraining the structure of quantum field theories from symmetry principles suggests this is the specific correct methodology. Whether the specific application to cosmology succeeds is the specific empirical question, but the specific approach is the specific right one. Let me now connect the mirror universe story to the specific question of observability, because I think the specific, most important and most honest thing to say about the Turok-Boyle proposal is that it is genuinely more testable than most alternative cosmological proposals. We've discussed multiple parallel universe scenarios in this series: the many worlds interpretation of quantum mechanics, the inflationary multiverse, the string landscape. Each of these involves specific physical realities, other quantum branches, other bubble universes, other string vacua that are permanently and in principle inaccessible to observation. The evidence for them is indirect at best, theoretical at worst. The Turok-Boyle CPT partner universe is also not directly observable. There is no causal connection between the two halves of the CPT symmetric pair. But the specific indirect evidence, the specific predictions about dark matter composition, neutrino masses, and the primordial gravitational wave background is more directly testable than the predictions of most multiverse scenarios. Consider the specific contrast with the string landscape. The string landscape contains approximately 10,500 possible vacua, makes essentially no specific predictions for the specific values of the fundamental constants in our vacuum, and is currently untestable in any specific direct way. The Turok-Boyle proposal makes specific predictions, specific sterile neutrino mass ranges, specific neutrino mass hierarchy preferences, specific gravitational wave amplitudes that specific existing and planned experiments can test within the next 10 to 20 years. This specific greater testability is the specific most scientifically important property of the Turok-Boyle proposal relative to competing cosmological frameworks. It moves the mirror universe concept from the specific philosophical domain, where it can neither be confirmed nor refuted, into the specific scientific domain where specific experiments can distinguish it from. Alternatives. Let me now tell you about what I think is the most important scientific lesson, that the Turok-Boyle proposal illustrates a lesson that applies beyond the specific content of the proposal. The specific, most productive theoretical proposals in fundamental physics are typically those that take a specific known established principle, a symmetry, a conservation law, a mathematical theorem, and follow its implications further than has previously been done, not introducing new principles, not adding new complexity, but extracting more consequences from what is already established. The CPT theorem has been known since the 1950s. Its application to particle physics and quantum field theory has been thorough and successful, but its application to the specific cosmological solution to the universe as a whole had not been systematically developed until Turok and Boyle. The specific 2018 paper is in this sense a delayed application of an established principle to a domain that had not previously been explored. This specific pattern established principle applied to new domain is the specific pattern of some of the most important advances in physics. General relativity is essentially Newton's gravity applied with Lorentz invariance. Quantum field theory is quantum mechanics applied to fields rather than particles. The Island formula is quantum error correction applied to black hole information. In each case, the conceptual advance came not from introducing new principles, but from applying existing ones more consistently and more completely. The Turok-Boyle proposal follows this pattern, CPT symmetry applied to the cosmological solution. The specific consequences, the paired universe, the sterile neutrino dark matter, the specific predictions follow from the specific principle more completely than had previously been explored. Whether this specific extension is correct is what the experiments will determine, but the methodology is sound. Let me now address the specific, honest uncertainty about whether the Turok-Boyle proposal is correct, because I think intellectual honesty requires being specific about what we do and do not know. The specific proposal is a serious piece of theoretical physics that has been published in peer-reviewed journals, has been cited by other theoretical physicists, and has generated specific follow-up work. It is not fringe physics. It is not speculation dressed as science, but it is also not established. The specific sterile neutrino dark matter prediction is not confirmed. No specific X-ray line from sterile neutrino decay has been definitively identified at the specific predicted energies. The specific neutrino mass hierarchy has not been determined. The specific primordial gravitational wave background has not been detected. The specific evidence for the proposal is currently theoretical. The specific internal consistency of the framework and the specific naturalness of the predictions. Internal consistency and naturalness are important. They distinguish credible from incredible proposals. But they are not sufficient for establishing a theory as correct. That requires specific observational confirmation. The specific status of the Turok-Boyle proposal is therefore a specific, credible, internally consistent, theoretically motivated framework that makes specific testable predictions, and that the next generation of experiments will either confirm or refute, not confirmed, not refuted. In the specific scientific limbo of proposals that are serious enough to investigate and not yet determined, this is the specific, honest assessment. The dramatic headline, scientists just discovered that the Big Bang created two universes, overstates both the certainty and the nature of the claim. Scientists proposed a specific theoretically motivated framework in 2018. The framework predicts specific things. The predictions are being tested. That is the specific accurate description. Let me now bring the complete picture together, what the CPT symmetric universe proposal means for physics, for our understanding of the universe's deepest structure, and what it connects to across this entire series. Throughout these conversations, from the gravitational wave background, through the black hole information paradox, through the dark matter problem, through the arrow of time, through the cosmological constant, through the cosmic web, a specific theme has emerged. The universe's deepest properties are connected to its deepest symmetries. The holographic principle connects the entropy of a region to the area of its boundary. The island formula connects information preservation to quantum extremal surfaces. The CPT theorem connects the fundamental discrete symmetries of quantum field theory to the structure of every specific process within it. The Turok-Boyle proposal extends this theme to the largest possible domain of the universe as a whole. If CPT symmetry governs every specific local process, it should also govern the specific global cosmological solution. The specific consequence, a CPT partner universe, is the specific, most direct application of the specific, most fundamental discrete symmetry to the specific, most expansive domain. Whether this specific extension is correct remains to be determined, but the specific logic is clear. The specific universe respects CPT at every specific local scale. The specific logical conclusion is that it respects CPT at the specific global cosmological scale too. The specific experimental tests of this conclusion are the specific next steps. Let me close with the most important and most personally significant insight that the mirror universe story provides. There's a mirror universe. The specific, technically honest version of this sentence is this. If the specific, most fundamental discrete symmetry of quantum field theory applies to the cosmological solution in the specific, most complete and consistent way possible, then the Big Bang is a specific CPT symmetric boundary from which two universes extend ours, containing matter and evolving forward in time. Its partner containing antimatter and evolving in the direction we call backward from our perspective. This is not science fiction. It is a specific theoretical proposal derived from a specific established principle by specific credentialed physicists at a specific respected institution, published in a specific peer-reviewed journal, generating specific follow-up work by other physicists. And yet, it is also not established fact. The specific predictions have not been confirmed. The specific theoretical framework requires specific development, particularly in the specific quantum gravitational description of the Big Bang singularity, where the two universes meet. The specific honest position is the mirror universe is a specific, credible, theoretical possibility, more testable than most competing proposals, taken seriously by a specific subset of the theoretical physics community and subject to specific empirical determination within the next decade or two through specific measurements of dark matter, neutrino masses, and the primordial gravitational wave background. This specific, honest position is more interesting than either the dramatic confirmation that the headlines imply or the dismissive rejection that excess skepticism would produce. It is the specific scientific position, neither premature confirmation nor premature dismissal, but the specific engaged, evidence-following uncertainty that defines science at its best. What makes the Turok-Boyle proposal worth taking seriously, what distinguishes it from the vast majority of mirror universe claims that appear in popular science, is precisely its specificity. Not a vague gesture towards symmetry, a specific mathematical framework derived from a specific established theorem making specific quantitative predictions about specific measurable quantities. The dark matter is either sterile neutrinos in the specific predicted mass range or it isn't. The neutrino mass hierarchy is either as the model predicts or it isn't. The primordial gravitational wave amplitude is either within the Lightbird sensitivity range that the model suggests or it isn't. These are specific questions. They have specific answers. The specific instruments to find those answers are being built. there's a mirror universe. Maybe. And the specific act of designing specific experiments to determine whether the maybe is yes or no, the specific act of taking a specific theoretical proposal seriously enough to test it rigorously is exactly what science should do with every specific, credible theoretical proposal that makes specific, testable predictions. The specific universe's deepest symmetries may be telling us something specific about its deepest structure. The CPT theorem may be not just a specific local constraint on specific particle interactions, but a specific global constraint on the specific solution that is the universe. If the universe respects CPT globally as completely as it does locally, then there's a mirror universe. And if there is, it contains specific observers who are also wondering whether their universe has a partner, who are also taking a specific symmetry principle with complete seriousness, who are also building specific instruments to test specific predictions, who cannot see us any more than we can see them, but whose specific physics is identical to ours, because CPT transformation preserves every specific physical law, and what is law for us is law for them, and what is law for them is law for us. That specific symmetry, that specific sameness of law across the specific asymmetry of matter versus antimatter is the specific most beautiful thing about the Turok-Boyle proposal. Not that there's a mirror universe in the dramatic science fiction sense, that the laws of physics don't care which side of the Big Bang you're on. That CPT symmetry makes both sides equally valid. That the universe, at the level of its deepest principles, doesn't distinguish between matter and antimatter, between forward and backward in time. Only specific observers within it do. And we are those observers, looking at a universe that appears to be made of matter, running forward in time with a specific history extending 13.8 billion years behind us. While if Turok and Boyle are correct, a specific partner universe extends in the other direction with specific observers made of antimatter running what they call forward, looking at a specific universe that appears to them to be matter, unable to see us, bound by the same specific physical laws, asking the same specific questions. There's a mirror universe. The specific evidence will come from the specific detectors watching the sky for specific X-ray lines, from the specific neutrino experiments measuring the specific hierarchy, from the specific CMB polarization satellites searching for the specific gravitational wave signature, from the specific universe telling us what it is, as it always does, to those who build the specific instruments to listen